Okay, so this is a timed challenge. You have 1 hour to establish an I2C communication between two peripherals of this microcontroller. This is an STM32 microcontroller, and the STM microcontroller that you use should have, for this experiment, more than one I2C peripheral inside it. I believe this one, which is the STM32F303RET6 microcontroller that is hosted on the Nucleo F303 board that I'm using, Nucleo F303RE to be exact. This one, I believe, has two or more, at least two I2C peripherals on it. And the objective is to establish an I2C communication between peripheral 1 and peripheral 2 of the same microcontroller, right? So I have to talk from peripheral 1 to peripheral 2 and vice versa, right? So I have to be able to send data from 1 to 2 and vice versa. That is the objective in 1 hour. Let's talk about what stuff you have to work with. Okay, so the first thing is definitely the IDE, the development environment that you're going to be using. My development environment of choice is the STM32Cube IDE, which is the latest and greatest at this point in time from STM. It has the ST-Cube MX software integrated inside it and an Eclipse-based development environment in it as well. So this will be my development platform of choice. The second thing I would need is the schematics that are downloadable from the STM website, and I'll try to put a link to it as well. But this would depend on which board you're using. That brings me, on the software side, these are only two things I believe at this point we would need. If we need something else, I'll look it up on the internet as we go. But yeah, these two things, just have them open before you start. On the hardware side, what you need is the Nucleo board that is hosting an STM32 microcontroller. And that microcontroller, whatever, you can choose whatever Nucleo platform you want, or even discovery platforms actually. It doesn't matter, as long as the microcontroller that you're using has two I2C peripherals on it, right? And so in my case, I'm using the Nucleo F303RE board, Nucleo board. Now that Nucleo board also has, which most Nucleo boards will have, a debugger and programmer on the board itself that is from ST itself. It's called ST-Link. And ST-Link is what will let you debug the program, program the microcontroller. For that, you need a USB cable. In my case, I need a mini USB cable. Most Nucleo boards will need a mini USB cable, but some, the L series specifically, the longer ones, they need a micro USB cable. So if you're using one of those, you would need a micro USB cable to start with. So yeah, that's two things: the Nucleo board, the USB cable, and the last thing you'll need, and the only other thing you need, is the wires, what's called the hookup wires. And these will let you connect externally on the board itself, but externally using wires, I2C peripheral 1 and peripheral 2. And as you know, I2C has two lines, the clock line and the data line. And so you would have to connect using two hookup wires. You would have to connect SDA and SCL of the first peripheral to the second. That's it. So you need one line for connecting SDAs together and the other line for connecting SCLs together. Okay, so that is all that we need. And at this point, I would say that get your timer ready, and I would like you to do this on your own before you see me do it, and then you can see my solution and see how you compare. And I want to bring it up that actually I have not previously done this sort of a loop connection for an I2C on the same microcontroller itself. So this would be my first time too trying to do it. So hopefully I make the 1 hour clock, and let's get going. Okay, we have the clock running. So the first thing I need to do is figure out which I2C connections that I need to connect to each other. So for that, I'm going to go to the IDE and open up a new project. While this is loading, I'm going to go to the schematics and just get acquainted with the morpho connectors. So the morpho connectors are on the sides of the STM board, and this is what I'm going to be using to connect the I2C1 and I2C2 peripherals. And you can see that these labels here, PA, PC, and all that. This is what I want to figure out, which one is SDA and which one is SCL. Okay, so I think the IDE is ready. Let's go back and find our board. So I'm going to go to the board selector and type Nucleo F303. Okay, so F303RE is my board. I'm going to select that, hit next, and I'm going to name the project I2C loop, and I just want a C. That's all good. Everything's default. Nucleo, everything's good. I'm going to hit finish. Initialize all peripherals, yes. Okay, so I have my basic project now. The next thing I want to do is, as soon as this project opens, I want to go to the STM cube, which is hosted inside this same IDE, and I want to figure out which are the two I2C peripherals I'm going to use. And based on that, I'm going to have to connect those two using the external wires to establish the I2C connection. Okay, so as soon as this is done, I'll be ready to go. Come on, let's do it. Let's check the clock. We are 58 minutes, so we're 2 minutes down, 58 minutes to go, and this is quite slow, slower than I remember it being. And meanwhile, I guess while this is loading, it's like every time I open the schematic, it's like, okay, all right, I'm here, I can do it now. Okay, so we are ready on the cube side. So I'm going to go to connectivity here, and I'm going to pick I2C1 and 2, right? We have 3 over here. I'm going to enable I2C1, and now let's enable I2C2. Okay, so I have both of these I2Cs enabled. I have a warning on I2C3, and let's see what that is. Just make sure that's not interfering. Status partly disabled conflict with I2C2. So you can actually only enable I2C1 or 2 or 3 at one time. So I've chosen 2. I don't need 3. We're good to go. Let's find the pins. Okay, so I2C1 SDA is right here. I'm going to write this down so I don't forget. So we have PB7. PB7 is I2C1 SDA. And then we have PA15. PA15 is I2C1 SCL. And then PA10. PA10 is I2C2 SDA. Okay, and PA9. PA9 is I2C2 SCL. Okay, so we have the 4 things we need to connect, and let's go here. So the first thing is PB7 is I2C1 SDA. Let's find PB7. PB7 is right here on pin 21 of connector 7. That is SDA. So that needs to go to, let me just connect a wire while we talk about this so I don't lose this pin. So I need a pin on CN7 pin 21. On CN7 okay, so we are 1, 3, 5, 7, 9, 11, 13, 15, 16, 17, 18, 19, 20, 21. Okay, so we are 21 pin number 21. We're connected, and then we have PA15 SCL. PA15 is where? Let's find PA15. It's on the PA12 is here. PA15. Oh, that's great. It has a solder bridge. So that's that's PB15. PA15. Wow, come on, PA15. Wow, it was all over here. It's like right next to where it was before. Okay, so it's pin number 17. So it's like 2 pins up from where I am. That's fine. So I leave a pin in the middle, that's ground, and the pin on top of that is PA15. Okay, so that is my SCL. So at this point, I have my red wire as SCL and my blue wire as SDA, and that is going to go to, let's find SDA first. That is PA10, 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 PA10 is right here. PA10, it's kind of hard to see when they move the wires around. So we have this wire coming up here, and that is pin number 33. So that for CN10, that's leaving 2 behind from the bottom, and we have the blue wire leaving 2 behind from the bottom, and then going to PA10, and then we have PA9. You would hope they put them right next to each other, but they don't. So PA9 is here, pin number 21 of CN10. So I'm gonna have to count from the top, I think. So 1, 3, 5, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so we have 21 is our SCL. So PA9 is SCL connected, PA10 connected, PA15 connected, and PB7 connected. So we have 2 wires, 4 connections done. How are we doing on time? Okay, so we're down already 8 minutes, and we haven't even started coding yet. So it's not looking too good right now, but let's try to catch up. So we have the 2 I2Cs enabled. Okay, so let's look at the configuration. Down here we can see I2C speed mode, standard is good, 100 kHz frequency is good, rise time, fall time. I'm not going to change anything. The only thing I need to change is that I need to enable the internal pull-ups for the I2C, because I don't have any external pull-ups right now connected, because I'm just using simple 2 wires to connect the one to the other. So how do I do that? I need to go to the system view, and I need to go to, I'm pretty sure GPIO. Let's see that. Let's see GPIO. And then let's go to I2C1. Okay, I hope you can still see this clearly. So I2C1 SCL PA15, I need to do a pull-up. So it is pulled up. Yeah, so the pull-up is enabled, and on the other side the pull-up is also enabled. And I just want to make sure everything else is good too. So we have speed high, pull up, and open drain, which is good. Open drain, speed high, pull up. Okay, we are good over here. The second thing I want to do is I don't want the pull-ups to be on both sides, right? I don't want both sides having pull-up resistors, because that's going to reduce the amount of pull-up. That's going to just go in parallel. So I don't need that. It's not going to hurt you to have both of them pulled up, but it's just, you know, it kind of shows that you understand the concept of why we need to pull up the resistance. If you don't know that, you have to go back and review that, the fact that it's based on capacitance. That's the hint I'm going to give you, because I'm running out of time here. So all right, so we are fine on the configuration side. I have pulled up the I2C lines. In terms of the only other thing I need to check over here before I generate the code is on the NVIC side. I'm going to go to NVIC, and I'm going to enable the global interrupts, even though if I might not or may not use them. I just don't want to have to come back here and enable them later. So I have these enabled, and that seems like that's actually all I at this point can think of that I need. So I'm going to just now Control S, save this, and it doesn't want to, so it's fine. I'm just gonna generate the code, and hopefully that saves it. So I'm gonna go to Project and Generate Code. Great, it doesn't show me that it has generated anything, but let's go to main.c. In main.c, okay, we have a generated code from the STM32 cube. We have the 2 peripherals loaded over here. Okay, now all I need to do is to be able to send data from, let's try from I2C1 to I2C2. And next we're gonna do I2C2 to 1. Okay, so what the first thing I'm going to do is figure out where where I have to put that code to transfer from I2C1 to 2. Okay, so let's go look at the driver files for this guy. So I'm going to go into drivers, and I'm going to go into the STM32 HAL drivers, and here specifically what I'm looking at is the I2C files, and that can be found right here, I2C.c and I2CEX.c. I'm going to open both of them. Okay, it doesn't want to open, so I'm going to leave it behind. I don't want it. It looks like none of them want to open, so I'm going to, okay, you have to right click. Some things just don't end up working out when you're short on time. It's like when you're short on time and every time you run into a stoplight. And when you're like running ahead of time, you're always running into green lights. Okay, so what I'm going to do is I'm going to just interrupt, I'm going to just use the polling mode because it's the easiest to do, and if we are able to beat the clock, then I'm going to try to attempt the interrupt mode and see if we can do that as well. So for the polling mode in I2C.c, I see that transmit in master mode an amount of data in blocking mode using I2C master transmit, and receive in master mode an amount of data in blocking mode using I2C master receive. And transmit, whereas transmit in slave mode an amount of data in blocking mode using I2C slave transmit, and similarly I2C slave receive. So what I'm going to do is I'm just going to call my I2C peripheral 1 as my master and 2 as my slave. So what I want to do is transmit from the master and receive it in the slave. Okay, so I'm going to go into search and try to find. I'm going to try to find where this function is. Should be in one of these files. What if I go to open declaration? Oh, it does work. Okay, great. So this is over here, transmits in master amount of data in blocking mode. All right, so that is going to block. That is interesting. So that is going to block, and let's see if this is going to work, because if it's going to block, I wonder if the slave, because it's the same processor that's running both of them, and if the master transmit blocks the processor won't have resources to read from the slave, which is both connected to the same processor. So let's see if this works. I hope it does. We're going to copy this. We're going to copy this onto the main.c file, and here I'm going to wow, it's like being very, very slow when you want, you know what, it's probably because I'm recording this and I'm clicking all over. No, but seriously, that's not fun. Okay, main.c, come on. It's like my cursor is not there anymore. Oh, wow. This thing doesn't do well under pressure, does it? Okay, I'm going to try to reduce the amount of open files I have. Hopefully that makes a difference. Hey, look at that. We got our cursor back, which is a good first step. I'm going to copy the, well, I'm not going to copy that. I'm going to copy, okay, I'm going to copy this guy here. And so that is my master transmit. And the next thing I need is the slave receive. So that's the master receive, slave transmit, and slave receive. Okay. Those are the two functions I need, and I've copied them into my main.c file. Now let's see what these functions need. So I need a return type first of all. So I'm going to put a return type here, call it status. And my status is what would capture what is returned by this function. And then I call the transmit function. I have to give it the I2C handle, which I can find up here. So I have that guy. And okay, so I have this, and then we have the device address. Okay, that is interesting. What is the device address that I'm going to be talking to? That brings up an interesting question, because I think that is programmed inside the peripheral driver here. Let's see that. Because I2C is a master-slave communication. It needs an address. The master needs an address for the slave to communicate to, right? So I'm gonna have to see how to put this into slave mode. Let's go into system view. Okay, so this is standard mode, and then we have, it doesn't say if it's master or slave. Let's see over here, SM bus disable. We have NVIC, DMA, GPIO. Parameter settings. Primary slave address. Yeah, so that's what I need. Primary slave address. So I can put that here. So let's say 0x68. That is the slave. If this is the slave. Primary address length. Yeah, so this is what it's saying, that it's, yeah, so I can configure the address of I2C2. So I've chosen I2C1 to be my master and I2C2 to be my slave, and I've chosen its address to be 68. And hopefully that would give me the ability to, now let's generate the code again. Do you want to save the unsaved files? Yes, please. So I got to remember it's 68 here. Let's go back to our main.c, and it's asking for the device address. So I'm going to say hex 68 as my slave address. Now it needs a data buffer. So I'm going to send it a data here. I'm going to say uint8 underscore t data to be sent. And then I'm just going to say 0x05. Okay, so that is the data that I want to send. And so for the pointer to the data, I'm just going to provide this guy. And then we have the size of the data, and it's just one byte that I'm sending. And the timeout, I'm going to be generous with it because I don't want to have some timeout failures just to start with, and I can fix that later. So that is my transmit command. Hopefully that goes from, so that is going from I2C1 as master to I2C2 as slave. Okay, so that is where we're at. Now I'm gonna set up the slave command as well, and then we have this one that is my slave, and that would be I2C2. So I'm just gonna copy that, and then we have p data. Okay, we have, all right, so this is the receive buffer. So let's make another buffer here, uint8 t and data underscore receive. Okay, and I'm just going to initialize it down to 0 first, and that is the buffer where the data is going to get stored after receiving. So data receive, and then we have The size is just again 1 byte, and then we have the timeout again. I'm gonna say be generous with it and say 5,000. Whoops. 5,000 milliseconds. Okay, so that should be transferring from the I2C peripheral 1 to I2C peripheral 2, and I think we're about to ready to do our first debugging session and see how it goes. So let's go ahead and hit debug here. Seems to have an error here. Let's figure out what it doesn't like. Probably forgot something. What did I forget? HAL status type def. What am I missing, guys? I have a bracket here. I have the bracket closed here. I have status equals colon here, ending while ends here. Yeah, and that looks good to me. And then we have everything terminated here. Where is this guy going? It's going here, and this is going here. Okay, I don't see the issue as of yet, unless there's something else that's missing up top, which does not seem to be the case. So expected expression before U ain't 16. But I gotta go check the, what is it wanted here? I have 1, 2, 3, 4, 5 arguments. 1, 2, 3, 4, 5 arguments. And here, am I missing an argument here? 1, 2, 3, 4. We have I2C, P data, size, and timeout. And these are 2 pointers. You have the size and the timeout. And yeah, I actually don't know what it's complaining about. We have the thing and the data and the 2 things. And we have this. Okay. All right. So in this case, when it's acting all weird, I'm just going to do a clean project. Let's do a clean. And let's try to do a build again and see if the error goes away. Yeah, so that was really weird. So the error was just because of some intermittent code, or the file was in some weird state that it didn't like it. Anyways, that kind of wasted a little bit of my time. So I'm down to 36 minutes left. I do have a build here. So let's go ahead and debug this. Everything looks fine. Just gonna leave everything as default. That's the good thing about STM32Cube IDE. I don't know if you remember from the Foundations initial lectures, setting up the whole IDE was quite a pain, but now with the STM32Cube IDE and before this with Atolic, it had become a lot easier. So right now it's complaining about not finding the USB ST-Link, so I just gotta go tell it to grab that, and that's because I'm using VirtualBox, so I have to transfer the USB control into VirtualBox, and now it looks like it has control. I'm going to debug now. Okay, looks like we're debugging. What I'm going to do is set up some just some variables to look at. So where do we go? I2C 1 and 2. I have both of them looking at over here. That is I2C 1 and that is I2C 2. We have our configurations, timings, and our transmit and receive registers is what would be really important to look at. And that would be the what we're what we're going to be taking a look at, and I'm just going to put a breakpoint here. The two other things I'm going to watch, I think I might actually already have. I might have these guys in variables. Yeah, already here. That's great. In variables, I have them displaying the data, and data receives what I care about. So let's go ahead and step through the code and see what it does. Okay, I2C 1 is getting initialized. All right, you see the configuration was written to I2C 1. I2C 2 is getting initialized. Configuration was written to I2C 2. I wonder if there's an address register here. Like, yeah, so it's probably sitting in one of these values is hosting the address, this address 68 that we wrote to it. It has to be sitting in one of these registers. I don't know which one it is exactly, but it looks like, comparing the two, it looks like it might be one of these, the OAR registers. We're gonna have to go take a look later on, but let's proceed. So we have our data that should be initialized now. So I'm gonna actually move this window down here so I can see. Yeah, okay. So we have the data initialized as 5. That's what I want. That's the data I want to send. And then we have the other data received initialized at 0. We're good. Okay, we're gonna now do a transmit. So we've got to keep an eye out of if the transmit fails or succeeds. So we're gonna look at the status, and we're also gonna look at the transmit register here of I2C1, and hopefully the receive register receives that value. So let's go ahead, and this is the moment of truth. Come on, 0x5. Nope, we have a HAL error. Okay, so that we have to debug now, and let's go ahead here and see why we are getting a HAL error. One thing you could quickly check if you do have a multimeter sitting there on your desk is if the I2C lines are high, pulled up high at 3.3 volts. That would be a good indication of I2C, at least the pull-ups working. That would be a good start with. So let us start with, let's look inside the function and see when all does it return an error. So we're not HAL timeout. We want to look at HAL error. HAL error is right here. It looks like I can look at a value. Okay, so what I'm going to do is I'm going to stop here, and I actually want to look at this guy, I2C error code, so I can get a better idea of what is erroring out. So right after here, I'm going to say I2C1 error code, and this is uint32. So uint32t, test it, and test what's going wrong. So I want to read test and see what's happening here, right? So let's go ahead and check. So this time I'm going to just break right on. Come on, it doesn't like it. I2C1. I think I might want this guy. Okay, I2C1. I'm actually able to access this in this file. Okay. Okay, we're running again. I'm going to run because I don't want to keep wasting time. So we are again back to HAL error, but this time I should capture in test. I should capture what type of error we have. and we can see we have error type 4. Okay, let's go see error type 4. What is this guy? It is error type 4. So HAL I2C error AF. ACE acknowledge error. Okay. Oh, yeah. Okay, so that is a problem. You see that problem? The problem is that is actually going to be a problem. We can't talk I2C. Oh man, that's going to be such a problem. Because the way I2C works is we have to send an acknowledge. We have to send an acknowledge from the slave to the master. And it's not receiving the acknowledge because it is stuck. It is stuck at figuring out I2C master transmit. And it's not going to get ahead of this, so it cannot actually run the slave. And this function is what's going to send the acknowledgement, because this is the slave sending the acknowledgement to the master. And till the time master doesn't finish, slave won't run, and master is waiting for acknowledge from slave. So this is not going to work out. Okay, we have to figure out something else. How are we doing on time? All right, we have 28 minutes left. What I propose we do is we go quickly back to the ways to run I2C. And in this, we have the polling mode we've tried. We could do a anytime this says blocking mode, we have a problem. We can't do that. I2C mode, non-blocking mode is what we're looking at. All right, so transmit in master mode an amount of data in non-blocking mode using transmit master IT. At transmission end of transmit, callback is executed and user can add his own code by customization of function pointer and receive. Okay, so these are looking like some promising things that we need to try right away. So I'm going to comment out this code because it doesn't work. And now I'm going to copy this guy, master transmit interrupt, and master receive. No, I want to do a slave receive interrupt. Okay, and this is also a non-blocking call, so that should be good. Okay, I have both of them. Now let's go see what they are made of. So we have transmit master mode. We have this guy, and address. Okay, this looks all good. This is easy to do. It's very similar to what we did before. So I'm just going to copy the prototype of the function here. And then we have slave. Let's go ahead and grab that as well. And in this we have the I2C, the data, and the size. That doesn't look too bad either. Let's go ahead and actually populate this because we know these values already. So let's do status equals master transmit in interrupt mode, and then we do HAL I2C 1. That is my I2C 1 peripheral, and then the device address we know for the slave is a 0x68. And then the data I want to send, I already have a data buffer, and then the size is just 1 byte, and that should do it. And then we have the status again, and we equal it to the receive this time, and we're receiving on I2C2. Okay, I2C2. And then we have P data. P data is our data receive buffer. Where to go here? Okay. And size is again 1 byte. All right, so we have the two things ready, but we're not done yet. Let's go back to the top, and there is another piece of vital information that it was talking about, which is the return call. Here, IO operation, and then we have at transmission end of transfer. This callback is executed, and user can add his own code by function customization of function pointer. So you know what? I'm actually going to copy this whole thing. And one other thing I want to read before I go forward is that what happens in the slave side. So at receive in slave mode an amount of data in non blocking mode. At reception end of transmit This is executed and again as an old code. Okay, so I don't think we need anything to do with the slave receive. When we're receiving, we might actually have to, because when the slave is done receiving, we might have to add an acknowledgement. I'm not sure how the function is written inside HAL, but we definitely need this. And I'm going to copy the slave one just in case we don't have to go back here again after we are done here. So here, that one, add a reception, end of transmit. HAL should copy this. All right, so we copy both these guys. Okay, and we have these here as reference. Okay, let's figure out where the callback is. So I'm just gonna hit define. I think it's gonna be a weak. Yeah, so it's a weak declaration. So that means we have to. This function should not be modified when the callback is needed. Blah blah blah. Should user file. That's fine. Structure that contains the configuration. Okay, all right. So I think what's happening here is we got to get this function. And we have to define this ourselves. There's going to be a callback that we have to define, and I'm going to do it right below the main function. Okay. Actually, I'm gonna look for a place where it says user code begin and end. So I'm going to add this guy here. And that is my master callback. The function other thing was saying is the function pointer. User can add his own code by customization of function pointer. What is this function pointer? Master tx cpld callback. Okay, so what I'm gonna do is I'm gonna say if this is if I2C equals I2C1, then this guy is my first master complete callback. Okay, transmission complete for peripheral 1. All right, we are running now. I'm going to proceed further, and we are at the line of transmitting. I'm just going to look at variables again, make sure status is okay, and I'm going to open up I2C 1 and 2. Let's see what we're doing here. All right, so the next thing is, yes, we have a HAL OK, guys. And that means I'm pretty sure we would have run, but I don't see, okay, we have the OK, but I didn't see the data of 0x5 that was transmitted out here. So I'm pretty sure that this guy will not be able to receive it then. Yeah, it looks like it's not receiving that value. Let's go inside and see how it sends that data over. Okay, so we're inside the master transmit, and in here we need to check how the data is transmitted. So we have that going into the buffer, and then where is the buffer going to? So see, one thing I'm still not completely sure of is this data being sent or not? And that is the issue we're having, because the data gets put into this pbuff pointer, which is sitting inside the main I2C declaration, the handle that we have. Now the I2C actually does get passed in here, and it does say that set n bytes to write and reload if this is greater than max n byte size. N byte size, max is 255, right? So that should not be a problem. How busy? And how okay? And meanwhile, you can see that there was nothing that was loaded onto the transmit register. So that is a little that is where the issue lies, and that's the one thing we have to solve still, is how do we send out that data on the line, right? How do we send out the I2C data from the master to the slave? And so for that, let's go back to the header file, and we see we have the master transmit that we're using. It does ask me for the data pointer, and I don't see anything else over here that could help me. So I wasn't able to beat the clock for 1 hour, but I did get a chance to go back and check why this was not working. And the reason was because of the address. Now, if you remember, the address we had set to 0x68, so 68 in hex. The reason that was not working is if you go inside the transmit IT function, you can check that the device address is what we're supplying it. It says that the device address, the 7-bit address value in the datasheet, must be shifted to the left before calling an interface. And that was the issue. We were not shifting it to the left. So how did I fix that? Well, I went ahead and first figured out what the shifted value would be. So if I go to a calculator and I type hex 68, that is over here, hex 68. How do I shift that to the left? Well, I just move everything over 1 to the left. And you can see that this then corresponds to a decimal value of 208. So shifted to the left, I have address as 208. So I made a 16-bit integer over here, universal integer, based on what this guy wants. So you can see that the device address is a 16-bit integer. And so uint16 address equals 208. And this is left shifted 0x68. Okay, and that is then supplied over here into the master transmit function. So that was the first and the only main issue that we had on why we were not able to send and receive data. The second thing, I went ahead and checked the connections, and those were all good. I checked the format in which we were setting, and that was also good. The only other thing I found is that it helps to add a little bit of delay, and I've just kind of mimicked a 500 millisecond delay over here, but this is a room for improvement. Add error handling here, right? So that would be a homework for you to figure out how you could, you don't want to use these kinds of functions, especially if you're writing production ready code. You don't want to have just blatant random delays every now and then. So they should be based on a certain calculation or based on a certain wait time for certain things. So over here, what we're waiting for is the master transmit to finish so that the slave can start receiving. And so I've just arbitrarily chosen 500 milliseconds. The right way to do this would be to add some error handling to check, has the master finished transmission? Were there any errors? Was the status returned as okay? If it's not okay, then let's handle the error and let's retry the transmission. And if it was okay, let's proceed further. And what is the next step? Well, the next step is what we had before, the slave receive interrupt. These are both non-blocking calls like we talked before. So the slave is receiving on the I2C2, and the value should be stored in this this variable that we have declared as data receive. And yeah, that is it, right? So let's try to run this and see how it works. So I have a breakpoint here. I'm going to add another breakpoint down here. And what I'm going to do is open up the variables over here, and then secondly the special function registers for the I2C peripheral over on the right. So that is I2C1 over here, and the next is I2C2. So those are my special registers. We're wanting to look at the transmit and the receive specifically. Those would be the two I'm interested in. A transmit for the master, I2C1, and receive for the slave, I2C2. Okay, so let's go ahead now and run. Okay, so we are now at the delay. So we have transmitted from the master. We're at the delay. Let's go ahead and let the slave send an acknowledgement and receive the transmission. So I'm going to, the fact that we have an arbitrary delay here and we have a breakpoint, the thing what happens is sometimes this won't capture like this time. And the reason is because this will time out, right? This sends some data and is expecting a acknowledgement from the slave in a certain amount of time, which is why this HAL delay 500 is very arbitrary. It should be improved, like I said before. But what's causing the issue as well is that we were breaking here, which is adding many seconds of delays. And by the time this master gives up, it's like, okay, there's no slave there with this address. I didn't receive any acknowledgement about what I sent. So it must not be there. So I'm just gonna quit the transmission, right? So I'm gonna remove this breakpoint and let's try this again. So you can see this time the transmission went through because we were not breaking in the middle, and you can see that we have hex 15 that was sent over the transmit to the slave over the wires that we have connected, right? The loop we've made with the wires. So the I2C1, the master sends hex 15 to the slave, and then the slave receives it and puts it in the data receive register, or data receive variable that we have declared. And that's how it works. And that is a working I2C connection between I2C1 and I2C2. And like I said, I'm leaving up to you to improve this. Instead of having an arbitrary delay, add some error handling, look to example code on how errors should be handled in HAL code. And this, as you're working on that, you will get more comfortable with the abstraction layer libraries of STM32. Now, there's one other thing that I'm going to do over here is this is one-way transmission, master to slave. Now I'm going to try to implement a transmission from the slave into the master as well. So from I2C2 to I2C1. So for that, I'm going to add a longer delay first. And that is because it's a new I2C transmission. So I'm going to wait for 2.5 seconds. Wait for previous I2C transmission to complete before starting a new one. Okay, and so that way the bus gets some time to get back to a normal state, which is a pull-up state. And then we're going to do a slave transmit. So I'm going to copy this over here, and instead of receive, I'm going to say slave transmit. And slave transmit, let's take a look at what it wants. So it wants the I2C handle, it wants the data buffer, and the size. So I'm going to make a new data buffer over here, and I'm going to say this one, the master to slave data buffers, and we have the slave to the master data buffers. Okay, and over here, we're just going to make a new buffer. And I'm going to send an arbitrary value of hex 54, and I want to receive it in the master. And I'm just going to initialize down to 0. Okay, so this is what I'm sending. So that goes over here. So I'm transmitting with a non-blocking call. So these are all non-blocking, right? So these are all non-blocking calls. So I transmit over a non-blocking call from I2C to the slave data of 1 byte. And then I have the arbitrary delay again. And followed by, I want to have a master receive. So instead of master transmit, we're going to do master receive. And that, yeah, we want it to, master is I2C1. We want the device address. We want the data buffer and the size. So the only thing we have left to do over here is to assign the data buffer, which is I'm going to make slave data receive. And you can see the address here is also, it's not the address that the master is sending to like it was over here, but it's the address where the master should receive the data from, the slave that the master should receive the data from. So we know that slave 68 is sending, and that shifted left corresponds to, this is decimal, by the way, decimal 208. And so decimal 208 is where I expect to receive the data from, and I'm going to store it in here. And that should be it. So I'm just going to do a, let's just call another HAL. I'm just going to call another HAL delay here, so I'm able to break right after. Okay. For the purposes of putting a break point. So that's it. I just want to actually put a breakpoint here. And wait here. So let's get rid of everything else. Let's build. And now let's debug. Okay, let's, we can now resume. And let's see what happened actually. So it looks like this time the first one was sent, but the second one wasn't sent. Let's try again. There we go. So the reason why sometimes this is not sent and that and why this is sent is because 500 might be at the very threshold. 500 milliseconds might be a very threshold of how long the transmission is going to wait before a receive acknowledge is received. So we probably should reduce this value, but again, this should not be based on, for the initial of kind of just implementation, it's fine to base it on just some random trial and error type values, for millisecond values for actually having a transmission. And once you have achieved transmission like we have in this case, then we have to go back and do the error handling properly. Now in this case, we were able to, let me just make this number format hex as well. So you could see what just happened is we sent from data from master hex 15, we received it in the slave over I2C, and then we sent the data 54 from slave and received it in the master over I2C as well. So that is a loop connection on the same microcontroller. We used two I2C peripherals to send data back and forth between them. And I hope this was a good learning exercise for you. We were not able to beat the clock this time, but it was a good learning experience. So yeah, that's it. So to sum it up, we established an I2C connection between two peripherals of the same microcontroller, I2C1 and I2C2 of the STM32F303RE-T6 microcontroller in my case. And we just sent some arbitrary data from I2C1 and into I2C2, and then from I2C2 back to I2C1. This is a master-slave configuration, so and you need an address to send it to. One of the things that we definitely learned over here is that the address, in not all cases, but in the case on how the HAL I2C code is implemented, we need to left shift the address before we supply it, otherwise it wouldn't work. And yeah, so other thing we learned that was important over here was the blocking versus non-blocking. And the reason we were not able to do blocking calls is because if we block at the transmit, how are we going to receive? It's the same microcontroller. If you have two microcontrollers talking to each other, or a microcontroller and a sensor talking over I2C, you could still use a blocking call, because you can block on the transmit, and the slave is a second device, so that's running its own processor inside it. So if you block the first one, it doesn't mean that you're going to block the second one too, right? That's its own processor. But then in this case, both the peripherals are connected to the same processor, so we cannot implement a blocking call. We have to implement a non-blocking call, which is why we used the master transmit interrupt call and the slave receive interrupt call, which are both non-blocking calls. And if you want to take I2C to another level, we do offer a I2C in-depth course where we're actually establishing I2C between a OLED display and an analog digital converter. So for whoever wants to take this to the next level, this was a simple loopback connection. But if you want to actually talk to different devices over I2C, which is more what you will see also in a lot of your projects, then we do have another course which goes into detail on that. But hopefully this teaches you good concepts about I2C, good understanding of I2C. On the hardware side, you need to remember that I2C operates over open drain, and open drain means that when none of the I2C devices are activating a bus line, which is either the SDA or SCL, the line is floating. So it's your job to pull it high when it's not being used. And that's why we used, on the master over here on the I2C1, we used the internal pull-ups to pull it high. And the job of the master of the slave would be to pull it low whenever it wants to send or receive data. So that's how open drain works. That is another important thing to understand about I2C. And I2C you'll see used so much because it's only, the great thing about it is only runs over 2 lines. So yeah, that was it on I2C.